All right, so first of all, before I start, I would like to thank the organizers for giving me the opportunity to deliver this lecture here. It's always a great pleasure to come to these in-person events. It has been a long time I haven't been on a conference, to be honest, and it's a great pleasure. I was having a great time here, and thank you very much. All right, so, well, I am based in Galway, yes. I am a postdoctoral bounty hunter, and currently my project is about the improvement of mechanical modeling in traumatic brain injury. So traumatic brain injury is one major cause of death and disability worldwide. And yes, so I'm mostly working on modeling and computational aspects in that area. Of course, you might ask yourself, so what is this chap doing at the SPIN workshop, right? I will come to that question later. So to achieve this project, I'm working in the beautiful University of Galway, which is located in the west of Ireland. So in short, I would say it's a medium-sized university in a medium-sized town. And I'm in the math department, which is about 30 academics all over, covering all the range, the topics of math. So basically, there are people working in algebra, in topology, in statistics, and a few people working in applied mathematics, and I'm one of them. So we have very little fluid mechanics, and that's quite a specialty of Galway. We have quite a strong group in solid mechanics. So don't be fooled by the color of the sky on this picture, right? We are in the west of Ireland, so we get a lot of rain. Huh? A bit of advertisement. In case you are looking for a good reason to come to Ireland, we will be hosting this solid mechanics conference in Galway this summer. So now the program of the conference has been set, but if you want to spend some money on a big conference registration fee, you are always welcome to do that. I think it will be a great conference, and I'm looking forward to it as well. So before my time in Ireland, I was a PhD student in France, well, my home country actually. And I was based in Marseille, where I did a PhD on nonlinear acoustics. And at this time, I was working on modeling the softening behavior of geomaterials. So that's actually the connection with the SPIN workshop. I was my PhD thesis was focusing on the softening behavior of rocks and concrete, and on the modeling aspects of that, all right? So this is a real blue sky, because we are in the south of France, right? So my talk will be in two parts. In the first part, I will give a summary of my PhD research, so on the softening behavior of geomaterials. And in the second part, I will give some recent results on the modeling of traumatic brain injury, and there are much more similarities than what you could actually think about. So I will show again this slide that I think you have been shown a couple of times this week already. I wasn't aware of this actually at the time of my PhD, but I think it shows something very interesting, which is the fact that sound speeds are not necessarily constant. Here we can see that after a strong earthquake, the velocity decreases and slowly recovers. And this is something that was observed in lab experiments a long time ago. Maybe it's something different, maybe it is really the same thing, but let's assume it's the same thing to make things simple. So most of these experiments were carried out on small samples of material that are vibrating longitudinally. So this is typically a sample of sandstone, which has a rod shape, and on the left side you have a piezoelectric sensor. On the right side, you monitor the motion using a laser vibrometer, for example. So Parisa has shown a lot of these experimental results yesterday, so I will keep it very brief. And I will describe the resonance experiment and the dynamic acoustoelasticity experiment. So in the resonance experiment, you will sweep the frequency of your piezoelectric sensor and increase the amplitudes. So if you start at low amplitudes, well, you get a bell-shaped curve, that is the resonance curve. And as you increase the amplitude, you see that this curve gets shifted towards lower frequencies. And this can be interpreted as a softening of the material. And in the dynamic acoustoelasticity experiment, which is a kind of build-up on this resonance experiment, you will add a local measurement of the time of flight across the material. And if you plot this with respect to time, you will see the drop of the sound speed. Then you are kind of in an oscillating state, equilibrium state more or less. And when you stop exciting your sample, you recover back to the initial value of the sound velocity. So this is pretty much similar to what is observed after earthquakes. Yes, so my goal was to try to model these features. And I was given a bit of literature, and first of all, the experimental literature often comes up with this kind of formula. So this formula is a constitutive law that is nonlinear elastic and viscous. So the stress, sigma, is related to the strain, epsilon. So typically, the law that links the stress sigma and the strain epsilon is not proportional. Here you have the stiffness, which is a proportionality constant, big E, but then you might have also other nonlinear terms that I have not written here. And of course, you have also some dissipation that accounts for the damping of the waves, right? So this is a typically viscous dissipation, just like in fluid mechanics. So if we look at the elastic part, here you can see the difference between a linear elastic law, which is materialized by this red line, and a nonlinear one. All right? So this is already quite a rich model, because this will describe, for example, enrichment through higher order harmonics, damping of waves, but it will not be sufficient to describe the softening and the change of the wave speed. So that's why there are some Ukrainian scientists based in Los Alamos came up with a modification of this model that will describe the softening. So their idea was to introduce this little parameter G in front of the elastic part, right? And this way, when G is equal to 0, we recover the initial constitutive law. But as G will increase, virtually, it's as if the stiffness, big E, has decreased as well, okay? So this will introduce a softening of the material. And then, of course, you need to find a way to compute the value of G. So they proposed a formula that gives the evolution of G in time. So it's a differential equation to solve. And this model was used in simulations. So just as shown here, we can see that, okay, as the wave propagates, the modulus of the elastic modulus decreases, right? And when we stop the excitation, it recovers back. So, okay, that's the end of my PhD thesis, and thank you for your attention. No, that's actually just the beginning. So I went to the library, and I looked at various books of solid mechanics. So I read about damage mechanics, but I thought that was not really what is happening in these experiments, because these experiments are happening at very small strains. So obviously not damage mechanics. And then I read about nonlinear viscoelasticity, and I thought, okay, that's actually pretty much similar to what is observed in the experiments. Because nonlinear viscoelasticity is a description, first of all, of a nonlinear behavior. Second, of course, of a behavior with transients, so relaxation times, and also dissipation. And of course, in a nonlinear viscoelastic solid, you can repeat the experiment. You don't damage your sample permanently. So that is pretty much coherent with what is observed in the experiments. And of course, we are also in these experiments at quite low frequency, because if I look at this sample and I look at the first mode shapes of vibration, actually the wavelength that corresponds to these mode shapes is much larger than this. Well, it's about the size of the sample. So it's much larger than all the small heterogeneities of the sample. So we are quite in the low frequency range, and therefore we can make the assumption that our material is behaving, let's say, in a conventional way. So it's an elastic solid, more or less, with some modifications. And, well, when we do modeling in classical mechanics, usually there are always the same steps. First of all, we write the kinematics of our problem. So what are the variables that describe the motion? Second, we write the balance law. So here we just follow Newton's laws to write the equations of motion. And second, we need to check that our constitutive law actually is physically acceptable. And that's thermodynamics. So if we write the conservation of energy and the principle of increase of entropy, we usually end up with the Clausius-Duhem inequality. So here this is for a material that depends on strain and also a small parameter g. So this is the Clausius-Duhem inequality that needs to be satisfied by, for example, this model proposed by the Vakhnenko people. This part is often, well, sometimes it's not done by authors, and that's actually a very bad thing. So if you get caught by messing up with one of these steps, you end up in the Guantanamo of continuum mechanics, right? So yeah, I'm just giving a small example, going back to this model that is both elastically nonlinear and viscous. So the stress, okay, it's the sum of a function of epsilon plus some viscosity and strain rates. If we inject this expression in the dissipation, so sigma minus du over the epsilon is equal to eta epsilon dot, and when we multiply it by epsilon dot, we get eta epsilon dot squared. This is positive, therefore our material is dissipative, and this model is physically acceptable. And then I went on doing the same thing with the soft ratchet model. So bad news, the authors didn't check, and I checked, it doesn't work. So this model is not physically admissible. Okay, maybe we can fix it actually, because this model is very good. I mean, this model has already a lot of physics in there. So to fix it, well, actually we just need to go back to the thermodynamics, and we can keep the same expression of the stress, why not? And if we do so, actually what we want to do is to integrate this differential equation du over d epsilon equal 1 minus g sigma of epsilon. If we integrate this, we get the expression of the internal energy big U. So the internal energy is expressed as follows. We have 1 minus g, then the strain energy, typically it can be a quadratic function of the strain, and then some integration constant that is a function of g. Typically it can be chosen as a quadratic function as well. And then we go back to the Clausius-Duhem inequality, and we want this inequality to be satisfied for every motion. So the simpler thing to do is just to take both terms proportional, because if these two quantities, du over dg and g dot, are proportional, then we get the product of the two gives a square. And the square is a sign quantity, which will be always positive. So that's what we have done here. And, well, then we just substitute the expression of the internal energy, and that gives us the evolution of the variable g. So what this evolution equation tells us is if the strain increases in the material, then the variable g will increase. And the variable g increase means the stiffness of the material decreases. So we have created some softening. And then if we stop the forcing and set the strain equal to 0, then we will get a relaxation, so an exponential relaxation towards the initial value of the stiffness, which is pretty much consistent, at least from a qualitative point of view, with experiments. Well, so far so good. Now we want to solve the equations to see what the model, to maybe kind of simulate experiments, right? So if we summarize the equations of motion, most of the time in continuum mechanics, we end up with a set of balance laws. So here I have written one for this model. So here the state vector includes the strains, the velocities, and this variable g. So on the left-hand side, we have a transport term, so with a flux F. And on the right-hand side, we have a relaxation term, little r, and a diffusion term with a diffusion matrix, capital D. And this is something that if you show that to someone doing fluid mechanics, he will be very happy because he knows how to solve these equations very well using finite volume methods. So this is just an example of such a scheme. So here we will first integrate the right-hand side of the equation with the relaxation and the diffusion matrix. And then we will solve the transport part with the flux F. Okay, so it's a kind of scheme with several parts, several stages. But the good news is that it's very easy to implement. And the second good news is that it's actually very well suited for solving wave propagation problems. So this is an example for a textbook on finite volume methods, which is focused on solving the very simple transport equation Qt plus Qx equals 0. So what it shows is that when you solve numerically a wave propagation problem, you need to choose your method very carefully. First of all, if you take a low-order method, so a first-order method, you will introduce a lot of numerical artifacts, such as numerical diffusion. So here, the analytical solution and the numerical solution are completely far off due to the numerical artifacts. And if you choose a higher-order method, things might not be much better, actually, because you will have a very nice resolution on the smooth parts of the waveform. But if you have some very brutal changes of your wave field, such as a shock wave, for example, then you will have a lot of oscillations all around. So that's not nice either. So finite volume methods actually are based on a very simple ideas to kind of combine both artifacts to, in a way that you reduce the impact on your waveforms. So in the parts where the wave will be smooth, you will choose rather the second order method. And in the parts where you have strong gradients, you will rather choose the first order method. And the result is shown here. So of course it's not perfect, it's full of numerical artifacts as well, but it's already much better. So that's what we did, and we performed some resonance simulation. So this is typically a similar resonance experiment to the one showed before. So we see this shift of the frequency towards lower frequency. This was quite an expensive simulation to carry out because at resonance, at resonance, the wave fields have growing amplitudes, but also the numerical artifacts. So if you don't want to be completely far off the resonance, you need to pay a lot for this simulation. That's why we then chose to actually carry out simulation in frequency domain using a frequency domain method, which I'm not going to present here. But this was much more efficient. And of course, we recover the full resonance curves, even parts that we couldn't really catch with the time domain method. And then we performed also some simulations of dynamic acoustoelasticity, and we were able to qualitatively reproduce this drop of the sound speed and the recovery of the sound speed. But I mean, the model was constructed in such a way that we would be able to do this, so there is no big surprise. The good news also is that this model is very easy to generalize in higher order dimensions, typically because this evolution equation on little g is a scalar equation that involves a strain energy and another energy. So if you want to do that in higher dimensions, you just need to replace the stress and the strain by a stress tensor and a strain tensor. So these are finite strain tensors, but you can do whatever you want. And just make sure that you choose the strain energy that is consistent with your elastic law, okay? And of course, we can reproduce also this softening in two space dimensions or even 3 dimensions. Good. What about quantitative agreement, actually? That's actually where my PhD thesis stopped, because we tried to match a resonance experiment with our model, and we see that at low amplitudes, the match was good because that's how we chose our parameters, and at high amplitudes, it's fine as well. But in between, the evolution is not exactly fitting the evolution of the resonance frequency observed in experiments. So to conclude on this part, first of all, the change of material property might not be a change of material properties. It's maybe just a nonlinear effect. Second, actually, I think to go beyond the state of art now, it would be important to look at what is the cause of this behavior. So from a micromechanical point of view, it is really a damage creation process. I don't think so, because it's happening at very small strains. If it's due to hydraulic effects, such as, I don't know, fluid pore pressure or these things, okay, why not? But then why do we observe this phenomena also on a dry sample? Okay, so probably it could be something related to internal friction due to the heterogeneity and the presence of grains. And therefore, that's why actually phenomenologically a viscoelastic model is very well suited to describe these observations. And then, of course, the sensitivity with laboratory conditions make the whole story much more complicated. And we're really in front of a complex rheological behavior to describe. So now let's move to the second part of my talk, where I will discuss a bit about traumatic brain injury. So first of all, what are the connections between biomechanics and seismology? So I think there are many. First of all, the most obvious one is that the dominant phenomenon is mechanical wave propagation. And this is the case both in biomechanics and in seismology. Typically, we cannot not access easily what is inside our head. We cannot access easily what is inside the ground of the earth. So this is something similar. That means we will use also imaging techniques to explore what is happening inside our head. And of course, when we do also laboratory tests, but for example, brain tissue, it needs to have some special authorization to access cadavers, and that's very complicated. And from the phenomenological point of view, actually, soft tissues are often described as nonlinear viscoelastic solids, which kind of makes a connection with earth material, which could also be considered nonlinear viscoelastic. The main difference now is the near incompressibility of soft materials, because in soft tissues, the compression modulus is about 1,000 times as large as the shear modulus, which means that, first of all, it's much more difficult to compress a soft solid than to shear it, and also the compression wave will propagate much, much faster. And the second thing is actually they have properties very similar to water. Well, our body is mostly composed of water, and these tissues are often saturated with water, so they should be considered multiphasic. Voila. So this is traumatic brain injury. Usually in medical science, we differentiate the primary injury, which is really the motion, like is shown in this cartoon, and the secondary injury, which is a swelling that can occur in very strong injuries. So this happened to a boxer actually during a fight, and the fight was interrupted too late when he already had this swelling of his brain, and he was taken urgently to the hospital to fix it. All right. So the primary injury can be caused by various types of motion. So it's really a mechanical problem. That's why I'm working on it. I mean, it's not something neurological or something like that. So the one cause is, for example, a shockwave injury. So this is caused by an explosion, for example. The other one is typical for car accidents, which is acceleration, deceleration of the head. And another one is direct impact. So this one, direct impact, is the one that was shown in the cartoon before, where, for example, you get hit or you receive a punch in a fight, right? So what happens in the head? So this is experimental data that was gathered on using a sample of brain, actually a fresh brain from a pork. And what they did is that they induced motion at the boundary of the brain, and they measured using a shear wave, echography sensor, what was happening a bit further from from the source. So the source is a very smooth sinusoidal pulse, just like this one. And this is what they record a few, well, not even 1 centimeter away from the source. And we can see that the waveform is now completely, is much more abrupt. So we have these velocity changes that are very brutal. And this is typical of a shock wave formation. So if this is the velocity and you take the time derivative of it, it means that we have very large accelerations. So just for order of magnitudes, on the left side, the source here corresponds to 25 g, so 20 times the acceleration of gravity. And on the right-hand side here, we are reaching already nearly 100 g. So these are accelerations that are huge and that can have terrible consequences on the state of the tissues, right? And this is actually one explanation for why some punches don't create an injury, whereas other punches that are much stronger can create an injury, because at low amplitudes, these shock waves don't form, but at larger amplitudes, you can create these shock waves that are causing huge damage. So I wanted to investigate a bit this shock wave formation. So I went to the literature, and most of the time, these tissues are represented as a viscoelastic material. So typically, this is a finite strain viscoelastic model, and most of the time it takes the form of a convolution product. So that's how we describe the dependence of the stress with respect to here, capital S, with respect to the history of the stress during the experiment, right? And the minus p c minus 1 term here, this is actually a term that accounts for the incompressibility of the material, where the little p is a Lagrangian multiplier for the incompressibility constraint. All right, so this function here is the relaxation function. It will account for exponential relaxation of the material. So typically, if we apply a stress history that has this shape, the resulting strain will be of this shape, so we will have these exponential relaxations towards the equilibrium value. Yeah, that's it. So I implemented this in a finite volume code. So on the left side, I'm inducing some sinusoidal motion, and the waves propagate from the left side to the right. So here, this is typically a case where we will see the formation of a shock wave, just as shown on the right here, where you have this vertical signal that, if you take the derivative of it, is a large, very large value. So the very remarkable thing about this is actually that if you look at the slope of the impinging wavefront, which is marked by these dotted lines, all the wavefronts decay. The wavefronts decay, but there is still formation of a shock wave behind the wavefront. And that is something that makes computations much more difficult, because in nonlinear acoustics, people used to estimate the distance of formation of a shock by using the fact that the wavefronts blow up. But here they don't blow up. So if you use their formula, you will find that actually there is no shock forming. But if you do the simulation, you see that there is a shock forming. So this was very surprising. So it kind of encourages people to use numerical simulation instead of using approximate formulas that are completely wrong. Very well. So I think I'm reaching, more or less the end of my talk right now. So the next steps are on this project, first of all, are to investigate how proelastic behavior can be even a further cause of damage and shockwave formation in the brain during motion of the head. Actually, our brain is pretty much like a very soft sponge. So that's one step. We have made some progress on this already. The next step is to model the swelling of the head after an impact. Swelling models exist in the literature, but they are completely disconnected from the impact, which in a sense, is not very useful if you want to study traumatic brain injury. So yeah, our goal is to find a criterion to express the fact that, okay, this punch is very bad and there will be swelling afterwards. So that's work in progress. And the last part is to implement a 3D code that is better suited to wave propagation problems than the actual 3D codes that are used in the community. Most of the time they use commercial finite element codes, but of course they are not very well suited to the computation of shock waves. Therefore, there are some code developments that are planned as part of my project. So first of all, I would like to acknowledge my my collaborators. So as far as my PhD thesis is concerned, Bruno Lombard, Nicolas Favry from Marseille have been contributing very significantly to this project. And in Galway, Michel Destrade is the one who got me interested into biomechanics, so I'd like to thank them now, and thank you for your attention. We can stay in touch using various channels if you like, and I'm happy to answer your questions.